And this is how I'm going to begin. Remember the differential calculus that was recently over started with this fundamental, the motivating question, rate of change. That was actually a physics problem, how fast something is moving. Then if you look at the mathematical part, you naturally enter the xy coordinate system, and the problem is translated to tangent line problem, right? So it's a geometry problem. And then I just pull it even out of the xy and look at it as a function itself. So that's the approximation problem. So these three things are introduced in the differential calculus. So how this one translates to integral calculus is that the rate of change problem going backward is an antiderivative problem, right? This is what we just did in the physics problem. How about the tangent line? How is the tangent line just switches? It becomes an area problem. It is not easy to see why the tangent line becomes area problem, and that's why it's called fundamental theorem of calculus. That connection is actually a serious one. And at the end of calculus 2, you're using this integral calculus technique. You learn why those quadratic approximation and linear approximation, even higher degree polynomial approximation, why they're a good one. And detailed analysis is introduced in that calc 2. All right. So right now we're about to enter area, the geometry problem. That section is 5.2. It's called Definite Integrals. Here, eventually we're going to introduce the mathematical definition of area of a region. Right? Not many of us actually question what do you mean by area of a region? You just say, oh, that's a formula, how I want to calculate the area of the region. Never actually ask this question. So we're actually doing that. Not here in 5.2, but it's going to be introduced in 5.3. Definition of area. So using something called Riemann sum. What we are doing in this section 5.2, we introduce a notation of an area, okay, when it has a curved boundary. So I think that's the next one. I'm going to introduce this definite integral notation. First, here's a picture. X-axis, and there's some graph like that. This is where A is, and here's B. Interval A to B. We even consider when A is equal to B. Then if A is equal to B, there's no interval, right? No region. So do you see that suppose this is a graph of X. You see this region that's created by this graph and the x-axis, or between A and this point right there. You see this region there? Because this region belongs to upper half plane, we consider this one as a positive region. Area of this region is considered positive. This one, x-axis and the graph itself bounds this region, right? So you can kind of imagine, oh, there's this area of this region, and because it's below the x-axis, we're going to consider that one even as a negative number, right? And here is another region, x-axis and the graph, and this is the end of interval we're considering, so we're going to consider that one as a positive region. So when you're saying that area of the region bounded by the graph of y equals f of x over the interval a to b, we're talking about area of this one plus area of that one plus area of that one, all of them together. But we respect that negative sign there, so they call it the signed area, or some other books is called net area, something like that. So, all right. Do you think the area of this region in here, magnitude, is actually bigger than this one in here? As I've drawn, I think it looks a little bit bigger. So if I add this number and that number, the positive negative will cancel out, right? But I think there will be still a little left over in here because this looks wider here. Then you're adding one more, a little bit more positive. So all together, if you add up all this area of this three region with a sign attached to it, I think you end up at some positive number. All right. This region is going to be denoted as follows. Stretch as symbol that we use for indefinite integral. They put this beginning number a and ending number b of this interval, and then put this f of x dx in there, and that's the signed area, total signed area. That's the notation. I haven't explained the meaning of the area of this region bounded by this curvy part. We don't know exactly what that means, but if that's understood, we denote that number like this notation. And there's obviously this area versus this antiderivative seems like at this point has nothing to do with each other, right? Going this derivative backward versus area of something has nothing to do, but they share the symbol because there is some connection between these two. That's why they use the symbol. But right now is a totally just separate problem. So that's that symbol right there. This is called definite integral. Definite integral is a number. Does that make sense? Definite integral is a number. It's this area add up and positive and negative. You end up at a number. How about indefinite integral? What was that? Well, what would be the better word as opposed to a number? This is a number. Functions, right? Yeah, functions are right. This is a number, and indefinite integrals are all the functions, the antiderivatives. All right, let me use this example. I have this nice example. We do understand the area of a region that is bounded by straight line, right? Such as triangle, rectangular region, or regions like that. We have no problem of understanding area underneath it because it's a straight line, right? We need a definition when it's not straight line, it's a curved bound, and then that's where we need a definition. But we already know the straight line definition, right? So let's think about this notation between 0 and 3. This is supposed to be the signed area, right? This is where x equals 0. This is where x equals 3. So I want you to draw a vertical line, and 0 and 3 make sense out of that region first for that number 1. Once you understand what region they're talking about, I want you to go ahead and compute the area of that region. If it is positive, take it as positive, negative, negative. All right? So that's your exercise number 3. Exercise number 3 will be all these parts, and I want you to grade this one 1 point, or that one 1 point, and that one a total of 3 points for the exercise number 3. All right? So go ahead and compute integral 0 to 3, definite integral 0 to 3. This is not about method. This is about how you just understood this notation. All right, how was part 1? Over this interval 0 to 3, so you go in 0 to 3 and draw a vertical line here like that. And think about what could be the region bounded by this left two vertical lines, and above and below by over this x-axis, and the curve here over the x-axis. So I hope you agree that region over 0 to 3 bounded by the graph is this triangle. Does that make sense? Yeah. So what is the area of a triangle? That's what I was asking. I forgot to emphasize it here. Once you get this magnitude of the triangle, you have to assign the sign. Is this a positive region or a negative region? It's all above x-axis, so we assign positive number there. So the answer is 3/2. Positive 3/2 is the answer for part 1. That's the meaning of this notation. Any question about part 1? So if you got this one correct, give yourself 1 point. If not, 0.5 or 0. Let's move on to the next one. I want you to do the second part, still in exercise number 3. Second part here. All right. Was that okay? Between 3 and 5, x-axis is like this much. And where is the curve? It's actually below. And draw the vertical line in here and making this end. And that's this triangle. Area of this triangle is 1, but because it's below x-axis, we assign negative, so we get the negative sign. So this complicated notation is representing the number, familiar number, -1. Okay? Any question about part 2? If you got that one, give yourself 1 point, and let's do number 3. What about everything from here 0 to 5? What is the meaning of this thing? Right, that's 3. I want you to write. If you already done it, you can just wait. Alright? Hope that makes sense. We don't change that to positive number. We add this positive number plus a negative number. So they cancel each other, leaving just 1/2. That's the meaning of this notation. Integral from 0 to 5 of this one, meaning of this notation is as follows. Any question about this notation? All right. Why did they make it so complicated? Why can't they just make it all the positive? The way this one is calculated is tied to the antiderivative. So if you actually have that sign built in, it was actually easier to algebraically handle rather than flipping the sign all the time. If you just want that area, of course, you will just consider 0 to 3 and 3 to 5 separately, not 0 to 5 altogether. But it all has applications. All right, that's the notation of the definite integral, not the definition of the definite integral, which is postponed to section 5.3. Then they introduced this some properties. I'm going to write that down. We're just going to focus on 1, 2, 3 here, because the other 4 and 5 is not that obvious. I'm just going to focus on what's obvious in here. Right. Let's look at the first properties. Definite integral going from a to a, right? You start from a interval and end up at a, and what kind of region is that? It's just one line. It doesn't even create a nice region, so area must be 0. Fair enough? So if you put same number. How about this one? A to b and b to c is a to c. For example, if I have this region there, I have a and b here, and c is somewhere in between. And there's this graph like that. If you look at this part here, a to b, a to, sorry about this, this is intermediate one is b, and last one is a c. So a to b, that is representing this area here, right? So you can write down a1 here. That's this area, a to b. Make sense? This one is area over b to c. So here's b to c. So that's that area, a2. On the right-hand side, if you go from a to c all at once like that, of course this area is the whole thing. That makes sense if you add a1 and a2, and that's going to be the area from a to c. So that's a1 plus a2. So we can split this area in half. I mean, some way in there. So I think it's easy to understand. You can insert this a to b and b to c. You can split up the definite integral like that. Even if it is a signed area, and it's not that hard. But it's easier to understand when it's all above like that. All right? Make sense? How about, I hope this, I wrote it like this, I hope it makes sense. If I write down a and b, it doesn't necessarily mean a is less than b, if it is a random letter a and b. So let's think about the situation. A is actually bigger than b. So for example, if I have 5 and 3, f of x and dx, this makes no sense. This notation represents interval from a to b. Interval only makes sense when you go 3 to 5, not 5 to 3, right? But again, because it's tied to the values of antiderivatives, and if they allow some definition of the meaning, if they put the meaning to this one, calculations are all convenient. You don't have to worry about a and b being unknown. Always have to carry this condition a, b all the time. you can put anywhere if you put a meaning to that. So because of this antiderivative connection, they decided to give a meaning to the symbol to this one, 3 to 5. This makes sense. 5 to 3 doesn't make sense, but we'll give a meaning to that. Look at 3 to 5 and flip the sign of the number you have. Okay? So if you see 5 to 3, what it means is really 3 to 5 is opposite values of the definite integral. So we gave a meaning to that. It's not really a theorem, rather it's a definition. So I think there's three things or something that I have to introduce at this stage with this concept of this notation barely introduced. Okay? So here's a little challenging part. What if I say 1 to 5 f of x there, right? dx. Versus it seems like there's no condition a and b with this understanding. So can I insert 1 to 7 f of x dx and 7 to 5 f of x dx? If it is 1 to 3, 3 to 5, it makes perfect sense. You know the 3 is in between, right? So if it is 1 to 3, 3 to 5, put it perfectly together. But can I just put any number such that this number is not even between 1 and 5? Let's say 1 to 7, 7 to 5. Will this work? Is actually equal to each other with this definition. Built onto it. So what this really means is that, well, 1 to 7, that's fine. But this is awkward, 7 to 5. So what do? You change to 5 to 7, right? So it's f of x dx, and what do? We have to change it to a negative if you change the order of these limits. Then what happens, think about this one in here. This is area, let's say it's a 1, and here's a 7. This is some function there. This is a 1 to 7, right? So it's all the area. How about here? 5 to 7 is a 5 to 7. So this one only indicates that. So if you take this area, subtract 5 to 7, you're left with 1 to 5, right? And that's what this one is indicating. So therefore, this one is still okay. Doesn't matter if B is actually in between A and C, you can always write in this way. So you don't have to worry about how this A, B, C are ordered. It's always true with this definition. Okay? That's the meaning of this nice property. Participate in answering these questions. So functions given like this, and A is here and C is there. This is y equals f of x. Let's look at the first question. The value. Which value is greater? Definite integral from a to b, so here's a to b, and definite integral from b to c, and here's a b to c. A to b is a bigger. It seems like a smaller area, right? But it's a positive. Therefore, as values, this is a greater number than this one, right? So that's the answer. How about number 2? Is a to c positive or negative? Here's a to c, positive, negative. What do you think? You have to use the size and all that. It's not exact calculation. Positive, negative. Negative, it seems like this is a positive number, this is a negative number. We add them together, but this magnitude of this one is a whole lot bigger. Therefore, altogether, it seems like a negative number. Correct? Any question? How about number 3? Which of the values is greater? This time is a to b, right? And what is the second one here? Not b to c, but it's a c to b, right? So this is a positive, but if it's b to c is a negative, but it's now switched to positive, right? Magnitude is still there. So which one's bigger? This one is a bigger one. Okay? We'll exercise about this note. Can use this notation. Any question? Very good. So that was the notation. And now what is this Riemann sum? This word showed up in one of the slides. You might have not paid attention to that part. But we use this Riemann sum to introduce the definition of area. All right?